Hello everyone, my name is Kathan and today we'll be discussing the problem Josephus Problem 2 from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. Now this question is a direct extension of Josephus Problem 1. So I suggest that you have watched the previous video on Josephus Problem 1 before you hop into this one, because I'm gonna reuse a lot of ideas that I've used there. Like, even if you don't watch it, it's fine, you'll still get it, but it's good if you have solved that problem first. Anyway, so we have a game here where n children numbered from 1 to n are arranged in a circle. During the game, repeatedly k children are skipped and one child is removed from the circle. In the previous game, every alternate child was removed, but here it's more of a general case. Every k child are skipped and a child is removed from the circle. In which order will the children be removed? Right, so it's very simple. You have n children given arranged in a circle. In a round, what happens is you skip k children and remove a child, right? And after you've done that, you again repeat the same procedure until there are no children remaining. So in the input, we have simply two integers, n and k, n representing how many children you have, numbered from 1 to n, and k meaning how many children you are going to skip before moving a children, right? And in the output, you have to print n integers, the removal order. The constraints here are like n can be as highest 10 power 5 and k can be as highest 10 power 9. So we'll talk about constraints in a bit in the example also when I discuss on iPad, but I guess the question is very clear. It's more of a generalized problem of the Josephus problem 1, right? In the previous problem, we removed like the previous problem actually was for n equals to whatever value and k equals to 1, right? So in Josephus problem 1, what we did is we removed every alternate children, but here k, you have a general k, right? So let's see how can we approach this question then. First things first, let's talk about constraints here. So we know that n can be as high as 10 power 5, so n was in order of 10 power 5. So what does it say? If you try to implement an order of n square solution, it's gonna cost you somewhere around 10 power 10 operations. But in 1 second, you cannot do more than 10 power 8 operations. So n square is out of the picture. So then you think about n log n, right? So n log n will work here. Then you think about order of n or something better than that, right? So you have to think in terms of this n log n or better than n log n. Fine. Now let's try to understand this question a bit more using the example test case that was provided to us. So n was 7 and k equals to 2. So what does n equals to 7 means? We have 7 children here. 1, 2, 3, 4, 5, 6, 7 labeled from 1 to 7. K equals to 2 means like initially we start our game from the first child. Okay. What we do is k equals to 2 means skip 2 child and remove this guy. Right. This 3 is gone. So you print this 3. Right. And once you remove it, the next game starts from the guy just after the removal guy. Okay. So you skip this 4. So you skip this 4, skip this 5, so you skip 2 guys, then 6 is gone. 6 is gone, you print 6. Okay, the next round starts from 7. So you skip 7, you skip 1, 2 is gone. So 2 is gone, you print 2. But the next round starts from 4. 4 is skipped, 5 is skipped, 4 is skipped, 5 is skipped, 7 is gone. Right? So 7 goes. And the next round starts from 1 again. Now 1 is skipped, 4 is skipped, 5 is gone. Right? So 5 is gone. Then you start again from 1. Right? 1 is skipped, 4 is skipped. Okay, 2 guys are skipped. Then you again come back to 1. So 1 is gone. 1. Right? And only 4 is remaining. So like if you want to simulate, you can do it. So 4 is skipped, again 4 is skipped, and then you remove 4. Okay, fine. So this is what you have to print, right? N equals to 7, k equals to 2. Like that is pretty simple. In a round, wherever you are at, you skip 2 guys from it and remove the next guy. And whenever you remove the next guy, the next round starts from the guy afterwards, right? So this is what you have to print, right? 3, 6, 2, 3, 6, 2, 7, 5, 1, 4. So this is the removal order is what you have to print. Fine. So how do you approach this question then? Now, if you have watched the previous video, like on Josephus problem 1, you might think, let's try that strategy. What was that strategy? We just simulated the game, right? So we just tried to remove every alternate children and collected all the remaining children for the next round. But that strategy actually worked because we were always sure that when we process some n elements, n by 2 were printed and n by 2 were left for the next game. But here, since k is a very general value, it may not happen that way, right? So in the previous question, if you remember, if you are removing every alternate children, that is if k was 1, we can be sure that we'll always process half of the array, right? In the given instance, we'll always process the array half. So if we have a problem Tn, we are sure that if we do order of n work, the remaining problem will be of n by 2. So this is what ensured that the time complexity turned out to be order of n. But here it is not guaranteed. Since k can be any general value, it can very well might be the case that even if you do order of n work, that you process the entire array once, you might be left with, you can say, an array with just one element less, right? It can be easily seen, like if let's say k was a very big value from the, like k was a very big value from initial position, let's say 1 2 3 4 5 so on till n, and k was very big value. So what can happen is in a round you will just process one element, and for next round n minus 1 elements will remain. Now what is this time complexity, guys? I guess you already know it. It is a time complexity of sort of selection sort or any other order of n square sorting based algorithm. So this turns out to be order of n square. So the previous strategy is not gonna work of just simulating the game. So now that we know that simply taking one pass through the array and collecting the array for the next round is not helping, we'll have to think something better here, right? So what are you gonna do? Let's think this question from the first principles, right? So to get an idea like what is actually happening. So don't worry about implementation as of now, but let's just see how the game is proceeding. So let's take the same example here, but at a more finer detail. So n is 7 and k was 2, right? So n equals to 7 means we have children 1 2 3 4 5 6 7. This time I'm also gonna write the indices here. So 0 1 2 3 4 5 and 6. Okay, and what do we do? I'll also write the reference answer above, so like it will just make sure that I don't do any mistake throughout the you can say removal. So 3 6 2 7 5 and 4, right? So this is the output that we should get. Fine. So what do we do? Initially we start from the 0th position. So initially the position that we start with 0, and which guy will be removed? You skip 2 children and remove this guy. So in other words, you add 2 to the current position where the game is starting, and remove the guy here at this position, right? And like to make sure that you don't go out of bounds through the array, what you'll have to do is you better mod it with the array size, which is 7, right? So what I am saying is, guys, for example, let's say k was very big. Let's say k was 10. But since the list is circular, what you'll do is if you do 0 plus 10, there is no 10 position here, right? But you have to cycle back. And if you want to cycle back, you use the mod operation, right? So if you just mod the position with the size of your list, then it's gonna give you the correct index. If you're confused, I'll show you. See, if let's say someone asks you to skip here maybe 6 children, right? So if from 0 you add 6, I guess it was easy. Let's say someone asks you to skip 7 children. So if you add a 0 plus 7 here, there is no 7 guy here, right? But you know this 7 actually corresponds to this 0. So if you simply mod it with 7 with the size of the array, it's gonna return you 0. For example, if someone asked you to add 8 to it, that is skip 8 children. Now there is no 8th children here to skip, but you know for the fact that after you have seen the 7 children, you skip this children and then you come here, right? So in other words, to 0 you add 8 and simply take mod of 7. This also gives you 1. It's a simple thing, right? So this is like, you can say, fundamental idea of circular array. You mod it with the array size to get the index in a range. So if you mod it, it's gonna return your index in range 0 to size minus 1. So this is the reason why you mod it with the array size. Fine. So with that is cleared, so the position that we'll have to remove the element is 2. So we remove this 3 guy. So 3 is printed. Now what will happen? Since 3 is removed, all of these guys are shifted. In other words, their indices change. Their indices now become 2, 4, 5, 6. And we again start from 4. Right? So after 3 is removed, we start from the next guy. So remember, we removed the guy at position 2, and now the game also starts from the position 2. Okay. So position is actually now 2. Now what next guy you have to remove? You skip 2 guys. So again you add 2. So 2 plus 2. Right? To make sure you don't go out of bounds, you mod it with the array size. But now the array size is what? The array size is now 6. Right? Oh, by the way, this should be 2, 2, 3, 4, 5, right? So 2, 3, 4, 5, right? So you mod it here with 6. In other words, this guy has to go. So this guy has to go. So you print 6, right? So this was the guy at position 4. Now again, you shift all the guys back. There is only one guy to be shifted, so this will actually take the position 4, right? So you again start the game from this position, position 4. Now, from position 4, you again have to skip 2 guys. So 4 plus 2, what is the size of this array? So this array is 1, 2, 3, 4, 5. So you have to do mod 5. So 4 plus 2 mod 5 is well, 6 mod 5, which will be 1. In other words, skip this guy, skip this guy, skip this guy. Oh, sorry. Skip this guy and skip this guy. So remove the guy at first position. Right, so this guy is gone. Right, so this comes out to be 1. And we print 2 here. Now, shift the array. Right, shift the array. So this will become 1, 2, 3. So the array size is reduced now. Okay, let's do one more. We removed the guy at first guy. Since all the guys are shifted, we again start the round from the first index only. So what is the next guy? It will be p equals to 1 plus 2 again. But this time we are going to mod it with, what is the size of the array? 4. To just make sure the indices lie in the range 0 to size minus 1, we just mod it with size of the list, whatever you have. So 1 plus 2 mod 4. So 3 mod 4 is what? 3. So this guy will go. Right, so then you print 7. Right, so this was actually 3. Okay, so this was position 3. So position 3 or 0 is one of the same thing, if you remember here, right? So like in this array, like whatever the array is remaining now, position 3 is same as position 0. Why? Because if you mod it with 3 again, it is going to return you 0. Fine. So the next part also you can start from 3. I'll show you. So 3, 6, 2, 7 and 5, right? So yeah. Okay. So now we start from position 3. The next round from position 3, you again add 2. If you again add 2 here, and now you have to mod it with 3. Why? Because that is the size of the array that is remaining. So mod 3, so 5 mod 3 is what? 2. Which indeed is the case. Effectively what you're doing is you are skipping this guy, and now removing 5. Fine. So now the 5 is gone. 5 is gone, which was at position 2. Right? So we print 5 here. Now, I guess we have done a lot of dry run here. Now it is a good time to pause and think what is actually happening here. Now let's try to collect some observations here. I think we have done enough groundwork here to actually formalize some approach here. Fine. So what are we doing? Like effectively, initially we had children from 1 to 7, right? Then we skip 2 children and we remove this 3. Then we start from 4. Then we again skip 2 children and remove 6. Then we start from 7. So whenever a round starts to remove children, you start from a given position. That is fine. But look at this inputs. Look at this input list, like a state of the input, how it is evolving. Initially, this is going from 1 to 7. Then it has 1, 2, 4, 5, 6, 7. Then it has 1, 2, 3, 4, 5, 7. What do you see here? These all are sorted, right? So the input list at the start of a given round is always sorted. So that's one good observation, right? So if you want to implement it, you might have to store input in a sorted fashion, right? So input has to be stored in a sorted fashion. Okay. What else? At every round you remove, right? So you actually skip 2 guys and then you remove. You skip 2 guys and then you remove. So you have to remove. To remove, first you find the position, the next position. That I guess we have already figured out. It's very easy to find. To find the next position that you want to remove, what you have to do is to current position, you simply add k and mod it with the size of the list, current size of the list. So next position can be found easily. Then you have to actually remove that element from your input list. So you need a efficient way to remove as well. Fine. So does this ring any bell in your ears? Like input has to be sorted, efficient removal. So I don't know about this, but if input has to be sorted and efficient removal is required, automatically my mind goes about can I use set here? Not even multi-set, because I know the elements are unique 1 to n just present once, right? So just set. You might think that, right? Because in a set, set always keeps the element sorted, and if you can remove it in log n, right? So this removal is very efficient. But how are you going to actually find the guy to remove like this at a given position, right? So set allows efficient removal, fine. Set keeps the input sorted, fine. But how are you going to actually find an element at a given position, right? Because that's what you have to do. You have to find the element at a given position and then remove it, right? So this normal set, it has everything, but it is lacking one option. Find an element at given position, right? And given position in range 0 to whatever the size of a data structure minus 1, right? Now C++ set doesn't provide any function for it, but there is this concept. So jargon alert, policy based data structure. Okay, so like it's a fancy name, but what it is like the GNU library has a special data structure which we call ordered set, right? So we call it ordered set for two reasons. Firstly, you can call it anything, but I'm calling it ordered set because it is, you can say, 99% similar to your original set. That is it has all the, you can say, functionalities provided by the normal set that you have in C++, like efficient insertion, removal, storing all the elements in sorted fashion and all. But what's important for is this data structure provides two important functions of out of which one is very important to us. The first function that it provides is find by order. Find by order, and it actually takes the index, right? So this is index in range 0 to whatever the size of your set is minus 1, right? And it's going to return an iterator to that element in log n time, right? So I'll tell you in a bit why this actually doesn't log in. So it's not happening magically. It actually relies on the internal implementation. The internal implementation of this set and ordered set is same. I'll show you in a bit, don't worry. So it provides this function, find by order, and there's one more function which we don't really care, which is called order of the key, right? So order of the key and element. So this guy actually returns the iterator to the element at that position, this index, and this order of the key actually returns the index of that element if it's present. Now here, if that index is not present, it's actually compiler dependent what it's gonna return, and here again the same thing. But like what you effectively know is like every time you are gonna search an element in range 0 to size minus 1, so this function is actually very helpful to us. So how are you gonna implement this ordered set? It's actually much more simpler than you would imagine. So I'll show you how you can implement it. You just have to do a couple of imports. By the way, this PBDS only exists for C++, so sorry Python and Java guys. This question, I guess it was made for C++ folks. So what you have to do is you have to actually import these two headers, right? And then you will have to define a type def for ordered set, right? So ordered set is just a name. You can give it anything you want. I could name it Kathan set, but it's a standard terminology. People name it ordered set. Now I'll tell you why this is almost similar to set, because first thing you observe here, it has this tree. Internally, if you don't know, set is also implemented as a tree, more formally a binary search tree. That is also coming here. RB tree tag. So what is this? This RB actually stands for red black tree. And if you don't know what a red black tree is, it's actually a balanced binary search tree. And the normal set that you have in C++ STL is also internally implemented as a red black tree, right? So this guy, and this is, you can say, ordered statistic. So why this ordered statistic existing is, like, if you don't know about ordered statistic, if you want to find kth smallest, kth largest, these are what we call ordered statistic. And here, if you observe what we are doing, we are finding by order, right? So that's why it provides an extra functionality, find by order, and that's why it is called an ordered set. We call it an ordered set. Otherwise, you can call it anything. But internally, it supports all these set operations. It's exactly a set, a red black tree, a balanced binary search tree. And the reason why balanced binary search trees are able to provide you all the operations, insertion, deletion, updation, login, is because these trees' height are always login. The tree height doesn't exceed login. And the way balanced binary search trees work is they actually search level by level. So you won't cause more than order of log n for insertion, updates, and deletions. But I guess if I discuss more than this, we'll be going out of the scope of this video. But all that matters to you is now we have a set which supports finding an element by position. So the question is done and dusted, right? So I hope you have understood the explanation till now. So what I'll do is we'll move on to the coding part here, because the coding part is actually very simple. What we do is we simply store all the children in a ordered set, and then we find the next position to be removed, we remove it. It's just a normal simulation that is left now, right? So if you have understood the explanation till now, please comment understood in the comment section of this video, and let's move on to the coding part. Alright, let's look at the implementation. But before we jump on to the implementation, like, feel free to watch the supplementary materials in the description box of this video on PBDS to get your feet wet on how this ordered set is working. But let's begin. So I have defined the headers here, and I have defined the type def for ordered set. One little thing I guess I forgot to talk was this less of int. This less of int actually ensures that the elements are stored in ascending order. If you make it greater of int, the elements will be stored in descending order, right? And then I've defined a type def for length, because we have to calculate length of array again and again, right? So I just want to shorten the code a bit. That's why I've defined a type def for length. Then what do we do? We start by taking the input of n and k, right? Then we defined our ordered set, right? So you can see the definition. I'm not specifying a data type here because I've already specified here less of int. If you want it to be a long set, then you specify here long, or there is a more general way to actually create based on a template. More on that in the description of the video. But yeah, here we only want to store integers, right? Because the numbers like n can be as high as 10 power 5, which very well fits in the integer range. So there is integers will be fine here. So ordered set of nums, we insert all of them in the set, fine. And then what do you do? We start the game from 0th child. So while there are children remaining to be removed, you first find the position of the next guy. So position plus k mod whatever the length of the set is. Then you find that element by position. So find by order of position. So this returns actually the iterator to that element, and this is actually a very efficient function. It works in order of log n being the size of the set. And then we print that guy, right? We have to print it, and then we remove it from the set. And this goes on until there is some guy remaining to be removed, right? So if you observe, this loop will run exactly n times until we have removed all the you can say n children's, right? And each iteration, what we do is we first calculate this. This is just a constant time operation, and here find by order takes log n, erase also takes log n. So all in all, this loop will run for n log n. And here insertions, like n insertions, each insertion causing log n. So here also n log n. So overall time complexity turns out to be n log n, right? And the space complexity is order of n because we are storing elements from 1 to n in the set. And yeah, I mean that's about this video, guys. So I hope you learned something new from this video. Like, I hope like many of you would have encountered this policy based data structures first time, right? So if you did find it helpful, please give it a thumbs up, and I'll see you in the next one.